Hey there, and welcome to this explainer. Look, if you're taking a course on compiler design right now, I want you to go ahead and just take a deep, slow breath. Seriously. Looking at a syllabus that's completely packed with automata theory, syntax trees, and parsing algorithms, it can feel incredibly overwhelming. It usually looks like this towering, impenetrable wall of math. But today we're going to lay down a very calm, steady, and clear foundation. We're looking at one of the absolute most fundamental concepts in compiler construction, and I promise you it is so much simpler than it sounds. So think about it. How does a computer actually read what you write? When you type out an elegant if statement or a while loop, you aren't casting some magic spell. A compiler is not this intimidating, unapproachable black box. It's really just a very careful, highly organized reader. Its entire job, literally the whole shebang, is to take the logic you've written in a human-readable format and patiently translate it into a structured format that a machine can actually use. That's it. It's just reading and organizing. To ground our exploration today, we're looking at the foundational literature of the field. We're specifically drawing from texts like Kenneth C. Loudon's classic, Compiler Construction Principles and Practice. This book, along with others like the famous Dragon book by Aho, Lamb, Sethi, and Ullman, well, they're the gold standards for understanding these systems. And let's be honest for a second, the Dragon book is totally famous for having a cover that makes it look like this mystical, ancient tome of forbidden knowledge. But really, it's just a manual for a highly organized reader. My goal for this explainer is to completely strip away that dense, intimidating textbook jargon. We're going to find the simple, physical, relatable metaphors hiding just underneath the surface of those pages. Section 1. Making sense of code. Okay, let's dive into this. Our very first step in this gentle deconstruction is to remove the mystery from the complex-sounding acronyms that you're going to encounter in your textbook's table of contents. In the world of parsers, you will constantly see letters and numbers grouped together like secret codes. But they aren't secret codes at all. They're just highly literal descriptions of a process. You'll hear the term LRK parsing quite a bit in modern computer science curricula. I know, it sounds pretty daunting, right? Kind of like an advanced algebraic formula. But LRK is simply made up of three distinct, highly digestible ideas working together in total harmony: the L, the R, and the K. If we can just understand these three tiny pieces one at a time, the entire concept of bottom-up parsing will suddenly click right into place. Section 2. Reading left to right. Let's start with the easiest piece. We'll look at the very first letter in our acronym, the letter L. This is the first step in understanding how the compiler physically approaches the text document you've written your code in. The L simply stands for left to right scanning of the input. And honestly, that is wonderfully reassuring, isn't it? When the compiler's parser begins to process your code, it works exactly like how you and I naturally read an English sentence. It starts at the top left of the file, reads the first word or symbol, and then just moves to the right. It doesn't jump around randomly, it doesn't start in the middle, it just calmly reads your code from left to right, one token at a time.
Section 3. Building from the bottom.
All right, so we have our L for left to right. Now let's gently shift to the letter R. Now, I will acknowledge up front that this is the exact moment where textbooks usually start to induce a little bit of syllabus fatigue, but stay with me here because the underlying concept is actually highly intuitive. If you look in your textbook, R stands for constructing a rightmost derivation in reverse. Read out loud, that sounds like an incredibly complex piece of academic jargon, but rightmost derivation in reverse is really just a fancy formal way of saying bottom-up parsing. Instead of starting with a massive abstract concept and breaking it down, the parser looks at the tiny individual pieces of your code and starts grouping them together. To give you a little spatial context for where this fits into your coursework, you'll notice Loudon's book separates these ideas structurally. Chapter 4 covers top-down parsing, which is often associated with LL parsing, where it starts at the root of a tree and works its way down to the leaves. But Chapter 5, where LR parsing lives, is completely dedicated to bottom-up parsing. It's just an entirely different philosophy of organizing information, shifting from predicting the structure to reacting to the pieces as they build up. I want you to picture building a house with toy blocks. You don't start by placing the roof in mid-air and building downward, right? No, you start with the tiny individual foundational blocks on the ground, the variables, the numbers, the basic operators you've typed, and you slowly snap them together. Those become expressions. Expressions snap together to become statements. Statements snap together to become a full program. You are literally building from the bottom leaves of a tree straight up to the root. Section 4. Peeking ahead just once. So, we're scanning left to right and we're building our blocks from the bottom up. We have officially arrived at the final piece of our acronym, the K inside the parentheses. Let's keep our energy nice and steady here because this last piece is actually a huge relief. The K represents the number of input symbols of look ahead. So the crucial point here is that sometimes, as the parser is building those blocks from the bottom up, it might get slightly confused about which blocks belong together right at that exact moment. To solve this, the parser just takes a quick peek at the next symbol coming down the line. It looks ahead just a tiny bit to make sure it doesn't assemble the wrong pieces together. And here is absolutely the best part. In almost all practical, real-world scenarios, that K is simply the number 1. For LR1 parsing, the compiler only ever needs to peek exactly one single symbol ahead to know exactly what to do. It doesn't need to read an entire page ahead. It doesn't need to hold the whole program in its memory to guess your intentions. Just one single token of context is totally enough to keep the entire build process moving smoothly. To completely lower your cognitive load here, Ludin's text actually reassures us with this quote. The cases k equals 0 or k equals 1 are of practical interest. When k is omitted, k is assumed to be 1. See, you don't need to worry about infinite, complex look-aheads. The math is contained. The scope is beautifully narrow. When you see LR parsing without a number next to it, it's literally just looking one step ahead. Section 5, a peaceful parsing takeaway. Well, we've deconstructed the acronym, and hopefully the intimidation factor has dropped significantly. Let's bring these isolated ideas back into a single, cohesive mental model that you can easily take with you into your exams and your programming projects. LR parsing is not some chaotic, magical translation. It relies on 3 peaceful, orderly steps. First, left-to-right scanning, reading the file exactly like you do. Second, bottom-up building, taking your small variables and operators and snapping them together into larger structures. And third, a single peek ahead, just checking the very next symbol to ensure it's making the right choice at the right time. Compilers aren't magic, folks. They are just incredibly beautifully organized. Which leaves us with a final thought to ponder as we wrap up this explainer. The next time you open your code editor and look at hundreds of lines of complex logic, are you ready to look at it not as a tangled web, but just as a series of simple, organized blocks waiting to be calmly read and assembled? Take this grounded, low-pressure understanding back to your textbooks, and suddenly, those complex algorithms will start to look a whole lot more like familiar friends. Thank you so much for joining me, and happy learning.